This is the 2019 AQA AS Further Maths paper, and it's the vector question. So, at the start of the question we're given the Cartesian equation of the line L1, and for part A we're asked to find the vector equation of the line. So in the Cartesian equation we've got an expression in terms of x equated to an expression in terms of y and to a term in z. And the key thing to remember here is that each of these expressions are equal to lambda, the constant or the multiplier of the direction vector. And so to form it into the vector equation form, then we need to find x in terms of lambda and y and z in terms of lambda. So first of all, we know that lambda equals x minus 3, and so x equals lambda plus 3. So we find an expression for y in terms of lambda. So it's 3 lambda minus 2, and then and so z equals. And so now we're going to find that the vector equation of the line R equals plus lambda times the direction vector. So for x the constant is 3, and the coefficient of lambda is just 1. For y the constant is minus 2 divided by 2, and 3 over 2 lambda, and for z constant is 2, lambda is minus 1. Let's have a look at part B. So in part B we're given a new line L2 which passes through 2 points, and we're given in terms of n, and we're asked to show that the two lines are not perpendicular. Now we know if two lines are perpendicular, so to show that they're not perpendicular we need to find the direction vector of each and show that when we find the dot product it's not equal to 0. So we've got the direction vector for L1, and that is from here, so it's 3 over 2 minus 1. How about L2? Well, we've just got 2 points that L2 passes through, and so what we've got there, we can find the vector from O to P and the vector from the origin to Q. So for O to P it's 3, 2, 0, and for O to Q that's it. So what we need, however, is the vector from P to Q. That will be the direction vector of the line going through those 2 points. And so P to Q, we can go along these known vectors, so it's the negative of OP and the positive of OQ. So that's OQ take away OP. So that's and so the direction vector for PQ equals, in terms of n, so that's the direction for vector for L2. So we're going to find the dot product of these, and what we're expecting is that it doesn't equal to 0. So the dot product, or scalar product, so it's the x term in those multiplied together, add on the y terms multiplied together, and the z terms. So that equals 3 times 3 over 2 is 9 over 2 minus n, and so that equals, the n's cancel out, which leaves us minus 3 plus 9 over 2, so that's minus 6 over 2 plus 9 over 2, so that gives us 3 over 2. Scalar product is not equal to 0, and so L1 and L2 are not perpendicular. Okay, let's have a look at B part 2. Okay, so on this one, it asks us to explain why they can't be parallel, just showing they can't be perpendicular. So how can they not be parallel? Well, again, they're parallel if the direction vectors, if one of them is a multiple of the other. And so what we can say is the direction vector for L1, which we just used, that's 1, 3 over 2 and minus 1. If that was true, then it would have to be equal to some constant times the direction vector of L2. And so that's And so for this to be true, let's see, we can compare the y direction vector. So that's 3 over 2 equals k times 3. And so k would have to equal a half. And so on this, on the z direction, minus 1 would have to equal k times n. So that's half n. And so therefore we can say n would have to be equal to minus 2. So if n is minus 2 and k is half, can we have it so that 1 is equal to k times this? So 1 equals a half times minus 2 minus 3. So 1 would equal minus 5 over 2. So this is a contradiction. It's not, therefore, not parallel for any values of n. Okay, last part, B.I3. And so we're given that theta is the acute angle between L1 and L2. We need to show that cos theta is equal to that. And two constants we don't know, we're not told here, but we're finding it in terms of n. So you need to be able to remember the formula for cos theta, and that is that it's equal to the dot product of two vectors, or the direction vectors, over the product of their magnitudes. So for L1 and L2, we've just found the dot product,